So normal distributions. I've drawn pictures of it before for you. We're talking about standard deviation and stuff. We calculated a z-score, right, in order to find like a percentile. And now we're going to dive into this even deeper, right? So we're going to look at it in terms of probability. So before we looked at the area under the curve as like a percentile. Now we'll interpret it as probability, and that's what those areas are going to be. We're going to look at that. So, it's a continuous random variable, a normal distribution. If we're looking at some value of x, that value can have actually an infinite number of values, right? So x can have infinite values. It can be any. It can be all kinds of decimals. Remember when we're talking about the difference between a discrete and a continuous variable, right? If a variable is continuous, we said that it could be like any number of different decimals, things like that, right? If it was discrete, something like the number of boating deaths per year or something like that. That's what I thought of. Right? That could be a decimal, right? Because you're not going to have half of a boating death unless they just think that's what popped in my head. So, we talked about this before, that if we look at a normal distribution, if we're to graph it, that's what it looks like. It's called the normal curve. You've also heard it called a bell-shaped curve, right, where right here in the middle of this line is your mean, which we represent as right? That is your mean. Mean is always the center, and the mean is always equal to the median. A normal distribution. So just like I said, you got your mean, median. I don't know why we talk about mode, it doesn't matter. But the mean and median are equal. Remember, it's symmetric about the mean. In other words, right? If I was to fold this thing in half, one side would match the other, right? Very important. The total area under this curve is equal to 1. And, right, for these areas these areas here and here, it looks like it's touching that axis, that x-axis, but it actually never does touch it. Over on those ends. We've also talked about this picture before when we were talking about what standard deviation is in terms of when we're getting a z-score. Remember we covered this, and I'll wind up writing this down at some point. Remember we said that we had z-score was equal to x minus your mean divided by your standard. I'm gonna have to write one of the standard deviation. And we came up with this z, right? And the z just tells us how many standard deviations away from the mean a certain number value is. So you guys have this picture written down somewhere at some point in your notes. And I don't really think you need to know a lot about the inflection points. Just know about where that curve starts. That's where your first standard deviation is, right? So this point is 1 standard deviation from the mean, and this is also 1 standard deviation from the mean. One is above, and one is below, right? This is 2 standard deviations below the mean, and this is 2 standard deviations above the mean. I really prefer to write this picture like this, right? There's 1 standard deviation, 2 standard deviations, 3 standard deviations, and this is 1 standard deviation, 2 standard deviations, 3 standard deviations. I think it's a little simpler to write it in that So standard deviations are always positive, right? And your mean will always be positive as well for a normal distribution. So yes. And your standard deviation is talking about the spread. How spread out is your data, right? So let's talk about which of these has the largest or the smallest standard deviation. So if I was just to base this off of the graphs, right? It appears that this one has a larger standard deviation. And it looks like these are about the same, right? But even though they're in different spots, right? What I'm looking at is the distance from here to here. If that distance, we could say that this distance looks about the same, right? So they have about the same standard deviation, but it's small, right? We look at from here to here, that's a bit larger, right? So they look about the same, but they have a smaller standard deviation than the other. All right, so which one has the greatest mean? And which one, let's ask that, which one has the greater standard deviation? A or B? So first of all, which has the greatest mean? A or B? A is correct. Okay. Which one has the greater standard deviation? B. Oh, yes, right. So A has a greater mean. If we had to estimate, we would say that A's mean is approximately 15, right? So for A, if we had to estimate, we would say the mean is around 15. Our standard deviation, we could try to look at where the first inflection point is. I don't know. It looks like maybe about there. I don't know. It's definitely going to be an estimate. Where do we think that is? Maybe about 16 and a half, something like that? What do you think? 16 and a half? And we could estimate the standard deviation is around 16 and a half. We're going to estimate. It's a definite estimation. For B, it looks like the mean is around 12. Well, let's estimate the standard deviation. Let's see. And it's all busy over there, so I think our first inflection point might be somewhere around here. Actually, maybe it's right about there, right? So we could estimate that our standard deviation, right, and that's the distance away from the mean. We estimate our standard deviation is around 9. Is around, oh my gosh, Why did I say 16.5 for this? Sorry about that. We're going to have to do 15 to 16.5 would be, sorry, 1.5. We went a little slow. And then, because we're looking at this distance, right? And then for our standard deviation here, we're looking at what is that distance, right? From 12 to 9, it's around 3, right? So standard deviation's around 3. Sorry. So we did this. We did it all at once. All right. So it's kind of hard to see these. Which one of these has the greatest mean? So when we're looking for mean, yeah, you're looking at standard deviation. Where's our mean for this one? Drop it right in the middle. So we're looking at our mean in, figure around 45. Drop this one down. So the answer, the greatest mean would be B, right? The greatest standard deviation is which one? C is right. It is tricky.
But why would it be greater if there's more?
No, it doesn't mean huh?
If there's more, A would be greater than
But which one what?
If it's A, if there's more, the median is greater, it has more than A.
But it's more down.
So B is has numbers.
Well, because it's between the numbers that is higher than the other one.
Are we talking about for standard deviation or for mean right now? So for mean, all we're going to do to figure out what the mean is drop down a line right through the middle, right?
Yeah, but what I'm trying to say is there's more means for A is more than
But for mean, all we're looking for is what number value we're at down here, right? So even though it's taller, all that means, because it's taller, all that means is that there are more, like, say if it was a set of data, right? Say this was people's height, or the height of someone, or something, the height of children, maybe, right, or something like that. All that means is that there are more values in our data set between 40 and 50. That's why it's taller, right? Because there's, like, more data. It doesn't necessarily mean that it means higher, because there's more data. Okay, what do we think the mean test score of this one is?
It is
60, 70, 80, 90. It looks like these are units of 10.
so maybe 6, 7.
Yeah, I think we could estimate that the mean is 675. How about our standard deviation? So what we're looking for is that distance. Huh?
No.
So that's 710. So what we would do is we would go 710 minus 675. That's what's going to give us that distance, right? So 35. All right. Oh, and there's the answer. Oh well. That's really weird. It is.
It looks like a thing.
I think so, because we were to drop it. Yeah, maybe 660. Maybe I don't draw so well. So, alright. That's good. You guys get the idea, right? We have done this before. We have looked at this picture as well, right? This is a standardized value, right? And what does that tell us? What does that z, this z, remember I told you, this z tells us how many standard deviations from the mean this value of x is, okay? That's what z is telling us. How many standard deviations away from the mean, above or below, that value of x is, right? So if I get a z value that's negative, I know that that x value is a certain number of standard deviations below the mean, right? That the x value is below the mean. And we have done this all. It's weird that it looks like you can't do it. So it says to use the standard normal table. We are actually going to just use our calculators on this, okay? And we will get to that. Next class is when we'll start using our calculators to make some calculations. But you're going to have an area close to 0 for extreme values. Like anything 3, at -3 or a positive 3, we're going to wind up with a very low area, right? And the same is going to be true for these higher values. And this is the point where we're going to get out our calculators. So next class, I get out calculators. I will show you how to calculate areas and the curves using our T9 slide. So we'll leave it here for now.